AC voltage applied to an inductor. Here we have an AC source connected to an inductor. We shall assume that this inductor has negligible ohmic resistance. Thus, the circuit is a purely inductive AC circuit. Let the voltage across the source be V is equal to Vm sin omega t. Equation 1. Using the Kirchhoff's loop rule, sigma epsilon t is equal to 0. V minus L di by dt is equal to 0. Equation 2. L di by dt is the self-induced EMF in the inductor and L is the self-inductance of the inductor. From equation 8 we have di by dt is equal to V by L is equal to Vm by L sin omega t. Equation 3. Integrating both the sides with respect to time, we get integral di by dt dt is equal to integral Vm by L sin omega t dt is equal to Vm by L integral sin omega t dt, or I is equal to Vm by omega L cos omega t is equal to Vm by omega L sin omega t minus pi by 2. Equation 4. I is equal to Im sin omega t minus pi by 2. Equation 5. The quantity omega L is equivalent to the resistance and is called inductive reactance and is measured in ohms. It is denoted by XL. XL is equal to inductive reactance. XL is equal to 2 pi FL, where XL is the inductive reactance in ohms, F is the frequency in hertz, and L is the inductance of the coil in henries. It can be seen that if either the frequency or the inductance is increased, the overall inductive reactance value of the inductor would also increase. As the frequency approaches 0, the inductor's reactance would also decrease to 0, acting like a short circuit. The inductive reactance limits the varying current in a purely inductive circuit in the same way as the resistance limits the current in a purely resistive circuit. The inductive reactance is directly proportional to the inductance and to the frequency of the current. From equations 1 and equation 5, we find that the current lags the voltage by pi by 2 or 1/4 1/4 cycle. Figure shows the voltage and the current phasors at instant t1. The current phasor I is pi by 2 behind the voltage phasor V. We see that the current reaches its maximum value later than the voltage by 1/4 of a period. When rotated with frequency omega counterclockwise, they generate the voltage and current given by equation 1 and equation 5 respectively. Let us find out power consumed, if any, by inductor. The instantaneous power supplied to the inductor is PL is equal to IV is equal to Im sin omega t minus pi by 2 Vm sine omega t is equal to minus Im Vm cos omega t sine omega t is equal to minus 1 by 2 Im Vm sine 2 omega t. The average power consumption over a complete cycle is PL is equal to average minus 1 by 2 Im Vm sine 2 omega t is equal to minus 1 by 2 Im Vm average sine 2 omega t is equal to 0. PL is equal to 0. Therefore, power consumption by an inductor over one complete cycle is 0.